Okay, so now having introduced ourselves to the Euler's axiom of the EQ. Thank you. So see, Euler's axiom, what it is telling us that of course on the right hand side of both the equations we have kinematic quantities, right? Kinematics. Kinematics means acceleration or rate of change of angular momentum. All these are kinematics related to motion. On the left hand side what we have, force system. It is about the force system. Euler's axiom is essentially doing this job for us. Force system on one hand, kinematics on other. But then you pay attention to the left hand side. What is appearing, what is representing the force system here? This is the net force, right? And this is the moment of all forces about O. Moment of all forces about O. So you can have a combination of 5 forces. Initially you can have a combination of 5 forces, force system 1, and that gives you one net force. And then you can have a combination of 50 forces, and yet it can happen that the net force due to those 50 forces could be the same as F. So what matters in Euler axioms is just the net force and net moment due to all forces. Now remind yourself, how did we define two equivalent force systems? Condition A was net force should match. Net force from force system 1 should be equal to net force from force system 2. And B was net moment due to all forces in one about a point equals net moment due to all forces in Fs2 about that point. Initially, when I introduced this idea of equivalent force system, I presented these two conditions as mathematical conditions. But in the light of Euler's axiom, you please see and make sure you understand that if two forces are equivalent according to this mathematical definition, then it is guaranteed the effect of those equivalent force systems on a given RB will remain identical. I am repeating. If you have force system 1 acting on RB, you have force system 2 acting on the same RB today and tomorrow, the motion of the RB will remain the same if the net force is the same and the net moment about O is the same. Indeed, that is the definition of two equivalent force systems. So, when I replaced a complicated force system earlier during our first lecture, when I replaced a complicated force system by an equivalent force system comprised of only one force and one torque, I am ensuring that the predicted motion of the RB will remain identical whether you put a 100-membered force system on the body or whether you put one membered force and one membered force and one membered torque on the same body. Okay, so the significance of equivalent force system is, I am writing here a statement, two equivalent force systems will cause identical motion of an RB. And this conclusion is based on Euler's axiom, on the two Euler axioms. So if my interest is only to predict the motion of RB correctly, why do I deal with a force system with thousands of forces and torques? I will first replace that complicated force system with a simple force system, maybe with one single force acting at a point of my choice and a torque, and I will still be able to predict the correct motion of the RB. That is the motivation why we studied equivalent force system. Alright, I hope this idea is clear to you. Alright, now we will move further. We know the relationship between forces and kinematics, Euler's axioms, and very soon we want to start solving some problems, predicting the motion of RBs. Before we go there, there are 2-3 more concepts which we want to understand. Those concepts will equip us better. We will be in a better situation to solve those problems. One of those 2-3 concepts is interaction of two RBs in Newton's third law. Newton's third law, you are aware, every action has equal and opposite reaction. Now, the kind of problems we want to deal with, we may have an assembly of RBs. Okay, we may have multiple RBs interacting with each other, multiple rigid bodies interacting with each other. And we would like to know what external force systems are acting on those RBs, one at a time. First we will consider one RB of the assembly. We would like to know what forces are acting on that. Then we will go to the next RB. We would like to know what external force system is acting on that, and so on. So if you have two RBs interacting with each other, I have shown a diagram here. The red RB, the red object is RB1 and the blue object is RB2. They are interacting with each other, and this is the surface of interaction. Now on RB1 we may be having an external force F and an external torque C acting on RB1. This we call as the applied force system on RB1. Somebody is putting this force system on RB1. On the other hand, on the blue RB, which I am calling as RB2, somebody else is putting a force system which is having one single force F and a torque acting. Okay. So this is the applied force system on RB2, applied force system on RB1. Now we want to separate the two bodies. Separate means not physically separate, but I want to look at the two RBs separately and draw their individual free body diagrams, right? So on RB1, of course this F and C are still acting. That is anyway known. But now that I have separated RB2 from RB1, I will have to put some forces. I mean, after all, RB2 must be putting some force system on RB1, right? When the two were interacting. When both were considered together, that force system between RB1 and RB2 was an internal force system, and we did not show them in this diagram. But if you focus only on RB1, besides the applied force system, force exerted by, or the force system exerted by RB2 will also have to be shown. That is what I have shown here. Similarly, when you go to RB2, there will be some force system coming on RB2 because of RB1, and of course whatever applied force system was acting on RB2, that is still there. That is still there, but these new distributed forces have come, and in general the force system will be distributed. The internal force system that we have identified here, they will be distributed because these two RBs are interacting not at a single point. In general, they will be interacting over a surface, and that is why you have a distributed force system. So now RB1 has these forces acting. But again, I do not want to worry about all the details of the distributed force system here. And I say that I am going to replace this distributed force system by a single force Fr12 and a single torque Cr12 at A. So this force I am putting at A. And of course this force is still acting on it. I have not shown it here, but I don't mean to say this is not existing. The applied force is still acting on this body. My focus of attention is what is happening at the interface of the two RBs. So I have replaced the distributed force system by its equivalent force system having one single force and one single torque. And then I have also put a superscript here, two characters, 1, 2. By 1, 2 what I mean? By 1, 2 I mean that this force and this torque 1, 2 is coming from 2 on 1. From 2 on 1. 1, 2 means from 2 RB2 on RB1. That's what I have shown here. That's what I have shown here. This is the force from 2 on 1, non-couple force, and a torque Cr12A. Now if I go to the second RB, again this F prime and C prime are still acting. I am not reducing their significance, they are still acting, but my focus of attention is what is the force system that is coming on RB2, this is RB2, from RB1. This is the force system. In general, it is a distributed force system. And I don't want to care about distributed force systems. I want to replace that force system by one single force Fr21 and one single torque Cr21. Acting at which point? Acting at point A prime. Here. A was here and A prime is here. Okay. I have written all these things here. Let's go over this once again. Fr12 is force exerted by RB2 on RB1, CR12A is moment of couple exerted by RB2 on RB1. When FR12 is placed at point A is part of RB1. Okay. A prime is part of RB2 and touching A, corresponding point on RB2, right? A and A prime are points belonging to RB1 and RB2 and touching each other. So physically they are at the same location. This is what it means. RAA prime is 0. Physically they are at the same location, but they are distinct points because they belong to two different RBs. And then I am using the symbol FR21 as the force exerted by RB1 on RB2. And CR21 A prime is moment of couple exerted by RB1 on RB2, where FR21 is placed at point A prime. So these are just the symbols for my understanding. Now I am invoking Newton's third law of motion, and we conclude that FR12 should be minus FR21. FR21 and FR12 should be equal but opposite in magnitude. This is coming from Newton's third law. And similarly, CR12 at A is minus of CR21 at A prime. Okay. We believe that Newton's third law is true. And if we believe Newton's third law is true, then we will be relating these four quantities in this manner. Okay. Now, these two equations by themselves do not tell us what FR12 or what FR21 is. It doesn't give us the value, but it reduces the number of unknowns. I hope you will agree with me. Here when I posed the problem, in general, I had one vector here, one vector here, one vector here, one vector here. 4 vectors I had. With Newton's third law, we are saying that these 4 vectors are not all independent. There is force to force matching with a minus sign. There is torque to torque matching with a minus sign. We will use these relationships extensively while doing analysis of motion in many scenarios in the coming weeks of this semester. All right. Just clean it up before saving it. Yeah, whatever I wrote, everything is there. It's just that while speaking, I wanted to highlight a few things. Okay, moving on. Free body diagrams. I know you already know free body diagrams. Consider this as a review. What is a free body diagram? A free body diagram is a diagram which shows all external forces acting on a body at their correct points of application and moments due to all external couples. In other words, torques. That's a free body diagram. In fact, I have been drawing free body diagram. When I was talking about equivalent force system, putting N non-couple forces, T torques, I was drawing essentially the free body diagram of the RB. But as I said, consider this as a formal review before we start using it extensively. So that is my first motivation, to formally review it. The second reason I want I want to touch upon this topic is to highlight some of the common errors, mistakes we make while drawing free body diagrams. We all are very familiar with free body diagrams, and yet there are some problems which some errors we make sometimes, especially during exams we see some types of errors. I want to highlight those at this point in the semester so that we don't make those mistakes. So let's consider an example. In this example, we have a platform. Okay, and this platform is supported by two ropes at point A and point B, and the ropes are tied on the top on the roof. There is one man standing here, the other man is standing here. Acceleration is acting downwards. The mass of the platform is big M, and the mass of this man is M2 and this man is M1. Both men can be considered to be exerting point forces on the platform. Strictly speaking, it will not be a point force. When you stand on something, your feet has some cross section, some area, you are actually putting a distributed force. But let's not go into that detail right now. These men exert point forces. Let's draw the free body diagram. Step 1 in drawing the free body diagram is identify your body of interest. Identify your body of interest, also called the mass system or simply the system we are focusing on. So what is the system here? It is platform. That's what has been asked. We have to focus on the platform only as our system. That is step 1. Step 2 is remove the surrounding details and show all external forces and torques. The moment due to couple is same as torque, so I don't want to use so many words here. Torques. Remove the surrounding details and show all external forces and torques acting on it. Surrounding details means what? Surrounding details are this rope being tied to the ceiling. These are surrounding details. I don't need those in my free body diagram. I don't even need the cartoon of these men. These are surrounding details. I don't need all of them. I'm going to remove all of them, but make sure that whatever forces and torques those surrounding details are exerting on my body of interest, they do come and appear on my free body diagram. So let's see, this is my claim is this is the free body diagram of the platform. First of all, I put mg, the weight of the platform. I put it at its center of mass. Actually, this is gravitational force is a distributed force system. I showed in the last class that the weight of any object is a distributed force system, but we can arrive at an equivalent force system with one single force acting at its center of mass. Right? That is the concept I am using here. Then I have replaced the ropes, two ropes I have replaced, and those details I have replaced, but I have to put the force that those two ropes must be exerting on my platform. Tension forces. I have marked those two tension forces as T2 and T1, and they are acting at their right points of application, at A and at B. I cannot put T1 here. That would be wrong. T1 has to be at point B. Then I have put M1G here, where the first man was standing. That point was C. At C I have put M1G, and at D the second man was standing. I have put M2G. So this, according to me, is the complete free body diagram of the platform. Okay, this is how we should draw free body diagrams. Free body diagrams are needed before we apply Euler's axioms. Alright, so this is a simple example. Let's consider one more example. And here I want to highlight a very common mistakes that all of us tend to do. So here what I have is a couple of sticks, a pair of sticks. Okay, this is stick 1 and this is stick 2. And these two sticks are leaning on each other, touching each other, resting on each other. And then there is somebody applying a force F here. And these surfaces are rough surfaces. It's not pin joint or anything, it just kept there. Okay. Sticks have negligible self weight. This is also given. Now here, if I have to draw the FBD of stick 1 plus stick 2 as the system, if I choose both the sticks making my system, then the free body diagram will be what I have shown here. Remember, in free body diagram, only external forces will appear. Only forces, torques, external to the system must appear. So the force that stick 1 is exerting on 2 will not appear here, right? Because 2 is also part of the same system. So this is the correct free body diagram according to my knowledge, my awareness. I have put F here, self weight is not there, so mg type of terms will not appear. Na is the normal reaction from ground at A, Nb is the normal reaction at point B, and then I have shown friction forces Fa and Fb. Okay. So in total 5 forces are acting on this system. This is fine. Now suppose for some reason I also have to draw the free body diagram of stick 1, only stick 1 as system. So what do I do here? At this point A, Fa and Na are appearing just like we had them here. But now that I have removed stick 2, the surrounding details surrounding stick 1 has been removed. So stick 2 also went away with that surrounding details. But the effect of stick 2 on stick 1 through forces and torques should appear on FBD of 1, FBD of stick 1. And that is what I am showing, two components of force P and Q. These are the forces that stick 2 exerts on stick 1. In general, two components, PQ. Alright, now if you have to show free body diagram of stick 2 also, for some reason I have to draw the free body diagram of stick 2 as well. So you have to now draw free body diagram of stick 1 along with free body diagram of stick 2. FBD of stick 1 I have already drawn like this. Now let's have a look at FBD of stick 2. So this NB and FB, they are in line with what I drew here when both sticks were my system. F is also appearing exactly in the same way. Now look at the direction of P and Q. So P and Q are forces. Now here P and Q represent forces exerted by stick 1 on stick 2. Alright. I have drawn Q from right to left here, whereas I drew Q on stick 1 from left to right here. This is not trivial. Please keep in mind, this is not trivial. Similarly here, I drew P vertically up. Here I have drawn vertically down. Not trivial. I am using a law which is guiding me that if P is vertically up on stick 1, it should be vertically down on stick 2. Which law I am using? I would have liked to listen from the students. Newton's third law I am using. What I showed on the previous slide. Previous. I am using this. FR12 should be equal to minus FR21. Newton's third law in action, in implementation. Okay, so this you should take care of. If you draw FBD of 1 like this, stick 1, and if you draw FBD of stick 2 not like this but this and this, you will never get the right answer. Never get the right answer. Okay, please keep this in mind. So in this way, all FBDs of individual parts of an assembly should be drawn in a self-consistent way. Self-consistent way. And that self-consistency applies here also. If you drew the free body diagram of the whole system like this, where NB was marked like this, and then if you go to FBD of stick 2 while solving the same problem and you change NB to downwards, wrong. Your FBDs have become inconsistent. Will never get the right result. So these things should be kept in mind. Okay. One of the common problems, common mistakes that we do. Moving on. Yeah, it's the same thing what I was saying. This will make an inconsistent set of FBDs, PQ shown on the other side. So that's one type of problem. Now this is the second type of common problem, and this is more common than the first one. See what happens here. Somebody asked you to draw the free body diagram of stick 1 plus stick 2. The whole thing is the system. And you drew the free body diagram like this. There is a mistake in this. What is the mistake? The mistake is that P and Q must not appear on this FBD. If stick 1 is the system or leave it. P and Q must not appear on FBD. Why? Because P and Q are internal forces to the whole system. So if you draw P and Q here and try to solve the problem, of course you will not get the right answer. Not only P and Q are appearing illegitimately here, there is another ambiguity. We don't know P is acting on which stick. It's acting on the left stick or it's acting on the right stick. Even that is not clear. So this kind of diagram is ambiguous in two ways. As I said earlier, first, internal forces are unnecessarily appearing, and then whatever forces you are drawing, it is not even clear it is acting on stick 1 or stick 2. So very avoidable. We must avoid this. Okay, very avoidable. Keep these points in mind. All right. What next? I said 2-3 more topics before we start solving dynamics problem. What is the next of those 2-3 topics? I'll have to go to another file. Alright. This part you please ignore. This is not relevant today. Please ignore all this. Please ignore this part. Next thing I want to talk about is various kinds of supports that we put on rigid bodies. And these supports, what they do is they constrain the motion of these RBs. I'll show you some figures in a little while, but let me first go over these points. See, when a force is applied on the RB, the support can generate a force system. And we will call this force system as the reaction force system. So I'm going to talk about something called reaction force system offered by a support. Okay, so many situations the motion of a rigid body of our interest is constrained by some supports. When we apply forces on RB, these supports also generate a reaction force system. Now, if our interest is to draw the FBD of an RB, we should remove the physical details of the support and replace those details by a reaction force system. Even though the reaction force system may be comprised of distributed forces and couples, for our analysis of motion using the Euler's axiom, all we need is the resultant force system with one force and one torque. One force and one torque. Further details of this reaction force system depends on the constraints that the support can impose on the RB. Okay, there are several points I made. Now these points will become clear when I show you this figure. Not a very high resolution figure, but I hope still you can make out. We don't need very high resolution here. What I am showing you here is, this is a steel pole, maybe a lamp post, or maybe an electricity transmission tower. Okay, this is an RB. Okay, and what we have done to this RB, we have fixed it in the ground using concrete. It's a pole which has been fixed to the ground with concrete. Now suppose this is my body of interest. Somebody is applying some force on it and I want to know how this object will move, or even if it is not moving, what is the condition under which it will remain stationary. So I need to draw the free body diagram of this body. Now whatever forces we are applying at the top, those forces will be applied force system, and I know them. Whoever is applying, they will that person will tell you that I am applying this much force. Your job is to draw the free body diagram. What are you going to do here? You will have to forget these details, whether it is concrete or brick or whatever, and you will have to apply a force system at this end, right? Now that force system I have been calling as the reaction force system. Reaction force system. You need to know precisely its form. Then only we will be able to draw an accurate free body diagram. Reaction force system. This reaction force system is generated by this support. So this is called a support. It is a support for the rigid body, and every support is capable of generating some reaction force system. We need to identify that reaction force system and put it on our free body diagram of this object before we can proceed ahead and use Euler's axiom. Now this kind of support, what you see here, this is fixed with concrete. It is actually called a fixed support, and I will show you in a little while. A fixed support will generate a particular kind of reaction force system. We will come to that. On this right side of the figure, I am showing another kind of support. What kind of support is that? So first of all, let's identify the body of interest. This is the rigid body of interest. Okay. I need to draw the free body diagram of this body. On this side, there may be an applied force system. There is some applied force system, CR at A. I need to know what kind of reaction force system is coming from this support. So this whole thing is a support. And this support is at this end, it's called a ball and socket joint. Now if you are told that this support is a ball and socket joint, again we want ourselves to be in a position to write or draw the reaction force system on the free body diagram. So this is a fixed support, this is a ball and socket joint. Both are supports, different types, different reaction force systems. Okay. So we are learning how to draw the reaction force system of a support. Now let's go back to the fixed support, what is called the big fixed support. So this is the body of interest. This is the body of interest, and it is grounded, fixed to the ground. I should draw it like this actually. Maybe this is fine. This is the body of interest, RB1. This is the applied force system, F1, F1, F2, some non-coupled forces, and then a torque is acting. We need to draw the free body diagram. Now in general, you can draw the reaction force system as one single force, let's call that as F reaction, acting at point B, and then an associated torque which I am calling as C reaction at B. In general, this will be the reaction force system. Now, if I am using a Cartesian coordinate system, x, ex, y, ey, z, ez, then F reaction can be written as this. So it has three scalar components, fx, fy, fz. Similarly, the reaction torque can be written in this manner, where you have three unknown scalars. A fixed support in general is capable of generating all these scalars. A fixed support is capable of generating all these scalar components. Okay, so your free body diagram in that way will introduce 6 scalar unknowns, which we will have to find sooner or later. But at least we know that 6 scalar unknowns will be there. Okay, now some other supports may have lesser number of unknowns, like ball and socket joint. We will go there also. The question is how to judge how many scalar unknowns are involved with the reaction force system that we are dealing with. How do we judge? On what basis we judge? Why am I saying that a fixed support will have 6 scalar unknowns? Why not 5? Why not 4? How do we make that judgment? I will explain to you how we make that judgment. See, if the x displacement of a point on the RB interacting with the support is opposed or resisted by the support, then Fx can be non-zero and Fx must be included on the FBD. This is the guideline. So you should go and ask the designer of the support, whoever designed that support, you ask whether your support is capable of resisting or opposing the x displacement of a point on my RB which is interacting with your support. If he says yes, my support is capable of resisting such displacement in x direction, then you should decide that in your FBD that reaction force system generated by the support can have non-zero Fx value. You should put Fx as an unknown on the free body diagram. If x displacement of a point on RB interacting with the support is not opposed or resisted by the support, then Fx is guaranteed to be 0 in the reaction force system. There is no need to introduce a new unknown on the FBD. Similar statements about y displacement and Fy and similar statement about z displacement and Fz. So capability to resist motion in x direction, if the capability is there, Fx should be, support is capable of generating Fx. If the support resists motion in y displacement, then support is capable of generating Fy. If the support resists motion displacement in z direction, then Fz, the support can generate Fz. This is the way we decide. Let's go back to fixed support. What is called a fixed support? If you go and ask the designer of the support, if I try to push so there should be a conversation between you who has to draw the free body diagram and the designer of the support. You ask, if I try to push B, so B belongs to RB1 and B is at the interface of RB and support. Okay. You call your designer of the support and ask, if I try to move B in X direction, will your support try to stop that motion or not? He says yes. immediately you should conclude that Fx must be included in the reaction force system. This should be taken as non-zero to begin with. You should not neglect that. Similarly, you ask, if I try to move B in the Y direction, will your support resist it? He says yes, you should retain Fy. Similarly for Z, he will say that it will resist and you should put Fz. This is what is a fixed support. Okay. So in that way you will judge whether Fx, Fy and Fz will be there or not. So this is the judgment about the force components. How do we judge the Cx, Cy, Cz components, the torque components? You should ask such questions, what I have here now. Look at this question. If the support opposes, resists the rotation of Rb along x-axis at the interface of Rb and the support, then Cx can be non-zero, must be included on the FBD. If the support does not oppose, resist the rotation of Rb along x-axis at the interface, then Cx can be put as 0 and there is no need to include this on the FBD. This is how you judge. So for all these judgments, you have to call the designer of the support. So in this support, if you call the designer again and you say that, you ask the question, so this is your x-axis. If I try to rotate this Rb about x-axis, will your support stop this? Will your support try to resist this motion? He will say yes, and that is why Cx can be non-zero, must be on the FBD. Then you ask the question, if I try to rotate the Rb about y-axis, will your support try to resist? He will say yes. You will say Cy to be included on FBD. And similarly, you ask the question, if I try to rotate the Rb about z-axis, will your support resist? He will say yes, because this is what a fixed support is. And then Cz must be on the FBD. So you ask these questions one by one, 6 of them you will ask. Depending on what the designer says, you will put that on the Rb. So fixed support is ultimate support which opposes displacement in 3 directions and rotations in all 3 directions. And that's why I said that for a fixed support, 6 scalar unknowns you will have to deal with on the FBD. There is no other choice. Now let me show you, and I'll end my lecture with this example, one more example. Let's talk about ball and socket joint. Let's talk about this. Fixed support I have already talked about. Ball and socket joint. So you see, this is the Rb of interest, and this is a special type of support which is called ball and socket, written here. You want to draw the FBD of the Rb here. You call your designer. If I try to displace this point B on the Rb along x direction, he will say yes, my support will resist. You put Fx. You ask, I want to move it along y direction, will it resist? His answer would be yes, Fy will appear. You ask whether if I move it along z, whether your support will resist? His answer will be yes. All 3 forces have come. So far everything is same as the fixed support. But the next 3 questions are going to be interesting. You ask, if I try to rotate my Rb along x-axis like this, you ask the designer, will your support resist it? His answer will be no. He has designed his support such that there is no resistance to the rigid body rotation in this direction. And that is why there is no Cx. Cx is 0. I have not drawn any Cx here. Same answer question you asked about rotation about y-axis, rotation about z-axis. His answer will be no, and that is why Cy and Cz need not be put on this RB. They are known, they are zero, trivial, not important. In this case, the reaction force system introduces only three scalars. Alright. So being aware of the kind of support is important before you can remove it and put a reaction force system on the FBD. We will talk more about it tomorrow. I stop here.